Hi everyone, I'm Chris and welcome back to the lecture on linear regression of this machine learning course. This section is about the model training. Here we have a model, like the linear model with a single independent variable x. This model is beta 0 plus beta 1 times x. In the previous section, we learned about different cost functions. A cost function is used to measure the quality of a model with respect to a given dataset. Here, we use a mean squared error cost function. This cost function for the linear model is displayed. On the right side, a hypothetical cost function with respect to one of the model parameters is sketched. Note that later we will learn that the shape of the mean squared error cost function for the linear model has slightly different properties than the one sketched here. The next step is to minimize the cost function iteratively. We start from arbitrary initial values for the parameters. Then the cost function can be minimized by a gradient based minimization. Let's take quickly a look on the properties of gradients. Here we consider the cost function h with respect to the two parameters beta 0 and beta 1. The contour lines, the lines of constant height of the cost function, are sketched. We can parameterize a contour line with a variable t. This gives the vector with beta 0 of t and beta 1 of t. So, continuous variation of t describes a specific contour line. The tangent vectors to the contour lines are given by the derivative of the line parameterization. The corresponding tangent vectors are sketched in blue. By definition, the lines of constant height for the cost function give h is equal to constant. So for our contour line, we have h of beta 0 of t and beta 1 of t is constant. The derivative of the constant right side with respect to t gives 0. The derivative of the cost function can be calculated according to chain rule. This gives the derivative of the cost function with respect to beta 0 times the derivative of beta 0 with respect to t plus the same expression with beta 1, and this is equal to 0. This can be written in vector notation. Highlighted in green are the derivatives of the cost function. This is the gradient of the cost function with respect to the parameters. Further, the derivatives of the parameters is the tangent vector. So, we see that the dot product of the gradient of the cost function and the tangent vectors of a contour line vanishes. This means both vectors are perpendicular to each other. So, the gradient is perpendicular to the contour lines, the lines of constant height. The tangent vectors are along the contour lines. So, the tangent vectors point along the direction of no variation of the cost function. The gradients are perpendicular to the tangent vectors. Therefore, they point along the direction of maximal variation of the cost function in parameter space. So, it seems a pretty good idea to use this direction to minimize the cost function. A gradient can be calculated by a finite difference approximation at a certain point in parameter space. Here, this point j is denoted by beta 0j and beta 1j. The finite difference approximation calculates variations of the cost function by small variations of the parameters. These differences are divided by the length of the corresponding small variations of the parameters. So, the gradient can be approximated at a certain point in parameter space. Let's start at a point denoted by j is equal to 1 in parameter space. Then we move along the direction of the gradient to a new point in parameter space. At this point, again we calculate the gradient and go along this direction. And so on. The corresponding iterative equation is displayed on the lower left. A new point j plus 1 in parameter space for beta 0 and beta 1 is the previous point j minus eta times the gradient at this point. The parameter eta scaled the gradient. This determines the step size for the gradient-based minimization. The success of gradient-based minimization strongly depends on the shape of the cost function. For example, does the cost function has a local minimum? If so, the gradient-based minimization could stuck in such a local minimum instead of finding the global one. For our optimization problem of the mean squared error cost function and the linear regression model, no local minima can occur. Even better, we can prove that the gradient-based minimization approach always converges to the global minimum. This is mainly because the cost function has a convex shape. The condition for a convex shape is that the second-order derivative with respect to one of the beta parameters is always positive. To illustrate this, let's take a closer look on two examples of cost functions. On the left side, a convex cost function is sketched. Its second-order derivative, the slope of the first-order derivative, is always positive. On the right side is a function which is not convex. Its first-order derivative starts with negative values and decreases. When the function reaches a local minimum, the first-order derivative vanishes. Then the function increases. This gives a positive first-order derivative. Further away, the cost function decreases towards a global minimum. Consequently, the first-order derivative becomes negative again, so the second-order derivative is changing its sign. That means it is not convex. Now, let's prove quickly that mean squared error is indeed a convex cost function for linear regression. We only need to calculate the second-order derivative for one of the terms in the sum. This is because the sum of positive second-order derivatives still is positive. Here we calculate the derivative with respect to beta 1. The first derivative reduces the square and brings it in front. The minus and x result from the derivative of the expression in the brackets with respect to beta 1. The second-order derivative is then pretty easy to calculate because this expression is a linear function of beta 1. This gives 2 times x squared. This is always greater than or equal to 0. Note that a similar calculation also holds for beta 0. So consequently, our cost function is convex, which is a pretty nice property. Unfortunately, for more general models like neural networks, the situation is much more complex. The gradient-based minimization will not always converge to the global minimum. It can happen that local minima occur. Further, the gradient can become very small so that minimization stacks, for example near a saddle point. And last but not least, the optimization parameters like the step size eta might not be well suited for the problem. On the left side is sketched what happens if the step size is too large. The minimization oscillates around the minimum and is not going directly towards the minimum. On the right side, you see a small step size. The minimization needs a lot of iterations to reach the minimum. This could take too much time. Section finished. If you like this video, please click the like button and consider to subscribe this channel. If you have any comments or questions, please leave a comment down below. And thanks again for listening. See you in the next section.